Hello, this is Alexander Powell, and I'm doing my final project for EML 3101. In this project, we will be using XFLR5 to design an airfoil, and with that airfoil, analyze a flow over 4 different types of wings. In this video, I'll only be covering one wing. So first, we're going to start with our airfoil design. The project specifies to use a NACA 2415 airfoil, and I choose 200 panels, and that's just more points on the airfoil right here. So we're going to change this color actually to be kind of a brighter color, be more like a blue. And this is for when we start doing some graphing. So after we have the airfoil, we're going to come here to module, and we're going to do Xfoil direct analysis. The analysis we're doing is over the wings. Eventually will be 20 meters per second. So first we need to do some airfoil analysis, as we're going to use this airfoil for the wing analysis. So we're going to define an analysis here. Type 1, Reynolds number we're going to set to 3 million. Hit OK. And we're going to be analyzing from -5 degrees to 20 degrees at an increment of 1 degree. Analyze here. Get our graphs, and then we need 3 graphs for the airfoil and the wings. We need a CL versus CD graph, which is this one. CL versus alpha, which is this one. And then we need another one that's not here. So if you actually just double click on a graph like this, we also need CL over CD with respect to alpha. So these top 3 are the graphs we will need. Before we move on to the wing analysis, we also want to do a batch analysis on this. It's going to analyze this airfoil at various Reynolds numbers, taking increments all the way up to 3 million. Again, we want to make sure the analysis range is the same as the one that we already analyzed, -5 to 20 at a degree increment of 1. You can also increase the iterations if you'd like, just to make sure everything converges. Hit analyze. And it finishes. So after that, you'll see the graph change because of all this extra analysis here. You can show and hide the various ones. Hide them all, show them all. You want to make sure before you do the batch analysis that you come to each graph and you actually right click it. You go to current graph and you can export it. You're going to need to export these 3 graphs before the batch analysis to get the values you need for the tabulation in Excel. Okay, but after you have those 2 analyses done, you can go back up into module. We're going to go into wing and plane design. We're going to come over here, hit plane. We're going to define a new plane. We don't need the elevator or the fin in this. We just need the main wing. We're going to hit define. Now the wing I'm choosing to do, it's going to have an aspect ratio of 12 with a taper ratio of 0.5. The root chord length is 1 meter, meaning the end chord length is going to be 0.5. We're not going to have any offset. Everything is going to be 0 besides these y values and the chord values. So to find the wingspan value, you need 2 things. For a tapered wing, the planform area is going to be the chord length at the root and the chord length at the tip. Add those 2 together, divide by 2, then multiply by the wingspan. And we know the aspect ratio is b squared divided by the planform area. So if you combine those 2 equations, in this case you find that the aspect ratio is equal to the wingspan over 0.75. So if you're solving for the wingspan, the aspect ratio is 12. You multiply that by 0.75. That makes the wingspan 9 meters. And the way XFLR5 does this, it's symmetric, so we need to divide that 9 by 2 to get 4.5. That's going to make each side of the wing 4.5 meters for a total wingspan of 9 meters. And you can see Everything checks out. We have a wingspan of 9 meters, aspect ratio of 12, taper ratio of 0.5. Last thing we have to do is make sure you click here and here so that it uses that NACA 2415 airfoil we analyzed in the beginning at both points of the wing. Hit save. Save again. Define an analysis. We're going to do a type 1 fixed speed. The free stream velocity we're going to be using is 20 meters per second. We also have to make sure we're doing a lifting line theory analysis, so make sure this is checked. Everything else you can leave the same. Save that. I also come to analysis settings, go to advanced settings, and I usually make this 200 above. I've set it at 500. Hit OK. Same thing in the analysis settings. We want to go from -5 to 20 at a degree increment of 1. I uncheck this at first. We'll hit analyze. So you see here, this is its analysis of each of the degree angles. Some of these cannot be interpolated as they're outside of the flight envelope. But now we can come in here. We can see the graphs again that we need. So we have this CL versus CD, CL versus alpha, and CL over CD versus alpha. And again, you're going to want to come to each of these, go to current graph, export for tabulation in Excel. Now for the wings, we also need, at 5 degrees angles of attack, we need to plot the variation of local induced drag coefficient, local induced angle of attack, and we'll use those two to find the local downwash velocity, and those are all over the span of the wing. So to do that, we come here to this op point view. This is why I didn't check store op point yet. So with op point in the graph setting here, you have your two options: induced angle, which is one thing we need, and induced drag coefficient, which is another value over the span of this wing. So we'll do the induced angle first. You can see how the y-axis label changes. Hit store op point. We can get rid of the sequence. Make sure this is at 5. Project states we need these values at 5 degrees. Hit analyze, and then we can see the induced angle over the span of the wing. So you'll come to here, current graph, export, and then you can double click on the graph and change it to induced drag coefficient. Same thing, right click, current graph, export graph. After that, you should have all the data that you need. We need this data to find the max CL, the max CL over CD value, the lift curve slope, zero lift drag coefficient, as well as induced drag coefficient, overall induced drag coefficient at 5 degrees, induced angle of attack, and downwash velocity. And this op point view is the local values across the wingspan at 5 degrees. So with all this analysis and all those graphs exported with their values, able to find everything that you need for the project. Thank you.